All right, so there were a couple of things, sort of assertions that that were made in this movie that get muddled up. And what I want to do is tease a couple of those things out. So one of the things that that we saw in the greenhouse effect simulation was that if you increase greenhouse gases, then the temperature of our planet kind of goes up, right? Like there was this connection between those things. But what we really know is that certain chemicals, the greenhouse gases, can absorb ultraviolet light and then re-emit it in a random direction. That's what we know. Because of that, we figured that this is happening. We have a whole bunch of evidence for this happening, okay? And then we also, so this is something that is generally accepted fact. We know that this is the case, okay? And then we also know with absolute certainty that over the last couple of hundred years, the average temperature of our planet has gone up. It's kind of gone up like this. It's like it's gone up and down, but and so there's times when you like, if you look at like 1960 and then 1968, maybe the temperature dropped during that time period. But if you look at overall, what you can see is there's this kind of trend, and the trend seems to be accelerating. It seems to be that temperatures are rising faster now than they were even 50 or 60 years ago, okay? This is factual. There's no debate about this. And I want to tell you how they get this information, because one of the things that's confusing about this is that this is looking at something called average global temperature. So what the heck is average global temperature? Like, how do you figure that out? Like today, it's cold. In July, it was warm. How do we know whether today is warmer than today last year or the year before? I mean, we can look at the temperature records, but it may be warmer here, but cooler in New York City, or maybe warmer in Nome, Alaska, but cooler in Panama. So how in the world did we figure this stuff out? And here's how we do it. It's actually, it takes an incredible amount of data, but if you have the data, you could do the calculations yourself with just a calculator. The way that we make these calculations effectively is that we measure the temperature in a whole bunch of spots all around the world at the same time every day. Now, I don't know if they measure it, they may measure it multiple times per day, or they may just measure it once per day. It's probably wouldn't really affect the data either way. They do make multiple temperature measurements a day, so we know, for example, what like the hottest part of the day versus the coldest part of the day. We have averages for those, but to get one number for average temperature, what you do is you start with a place, like Corvallis, and you measure the temperature on a given day, maybe just once. Let's say we measure it at noon. So let's say today it's 43 degrees, okay? And then you take that temperature and you add it to the temperature that was taken at the same time at hundreds, thousands of cities and other locations throughout the world. And then you divide by that number of locations. So you take the 43 of Corvallis, you add it to the 52 of New York City, you add that to the 18 of Nome, Alaska, you add that to the 81 of Panama City, you add that to all the locations, and then divide by the number of locations. And we get one average temperature for the entire globe at noon on one day. And then we do that all year long. And we take those numbers, we add them together, and we divide by the number of days in a year. And what we end up with is one number that tells us, on average, what the temperature of the whole planet was over the course of a year. Now, the actual way that they do that is more complicated because they can. They have so much data and so much computing power that they've got, like, they know, they have temperatures like to the minute. I mean, you know, you can look up on weather.com and see what temperature it is right now, basically anywhere in the world. All that data is being stored and all that data is being analyzed, but what I just described would be probably, you know, for the kind of work that we would do in this class, be just as meaningful. And so what that means is, if we say, okay, in 1892, for the whole year, we added everything up, we did all the averaging, and this was the average temperature. In 1900 it was here, in 1930 it was here, in 1945 it was here, in 1981 it was here, in 1996 it was here, and in 2010 it was here. That's where this graph comes from. So the thing about this graph is, it is fact-based. There's no opinion here, and there's no politics. And this is where, what I want you guys to understand is, this is data. This is something that's been determined experimentally. We know that if we increase greenhouse gases, that temperatures in general will increase. And then there's this realm of what we call predictions. And this is all done through what we call scientific models. And what's really interesting about predictions and scientific models is that they're not all the same. And so this is where the politics comes in, right? So basically, we use our models to try to make some predictions about a bunch of things. One thing that we're trying to predict is what's going to happen in the future with temperature. And we don't really know. We can't. But we have some pretty good models, and we have some ways of testing them. And what we think is that it's very likely that global temperatures will kind of look like this. At the most, they'll keep going up for a while, and maybe 100 years from now, they'll hit this like super high point. At the least, they may actually drop a little bit and end up here. And we have, you know, done a bunch of really complicated statistics and math, and we think there's like a 99% chance that we're going to end up somewhere in this range. And it's also possible for us to kind of narrow that and say, well, what's the most likely? And what we have right now is, I'm just like sketching this out. This isn't really what it looks like, but this is just an example of what it might look like. What we think is, this is sort of the most likely scenario, right? Is that temperatures are going to continue to increase, and then at a certain point they'll start stabilizing. This is what we think. And this is made using a model, and we'll talk about that in just a second, what models mean and how they're used and stuff. So this is one prediction. This is a prediction. And one of the things that, that can happen with predictions is that they're always wrong. Always. 100% of the time, predictions are wrong. The only question is, by how much are they wrong? So we'll come back to that in just a second. Another piece of information that goes into this is why. Why is this happening? We think, with reasonable confidence, like very high levels of confidence, that this is cause and effect. In other words, we think that the increase in greenhouse gases is what's responsible for the current increase in temperature that we're seeing and any future increase in temperature that we're seeing. Again, we can't be sure, but we think that our models seem to indicate that that's the case. Another prediction that we're making, or inference that we're making, is that it's humans that are causing the increase. So we think that burning fossil fuels is leading to an increase, in particular, in carbon dioxide, which is one of the greenhouse gases, right? And then the last set of predictions that we're making from all of this stuff is what is going to happen, right? If the global temperature goes up, then what? Are all the glaciers gonna melt? I mean, like that movie kind of makes it look like all the glaciers are gonna melt. Are animals gonna die? Are plants gonna go extinct? Like, what is gonna happen? So what happens to our planet as a result of all of this? And all of these things, all of them, are predictions that we make. And we have a certain level of confidence in these predictions based on how well they've played out in the past, how much data we have to support our conclusions. And basically, we have like the highest confidence in this. We have reasonably high confidence in this. We have very high confidence in this. And this piece we're not sure about. We're pretty confident. We're making predictions that are probably somewhere between 60 and 80% likely to occur. But that's a lot less than 99%. Okay? And these predictions often are talking about things that are going to happen long in the future, 20, 30, 40 years from now. Which means it's really hard to get a sense for whether those predictions are accurate in the short term. We can say sea levels are going to rise by 3 feet by 2080, and then we have to wait. And when we get to 2080, it's going to be wrong, because predictions are always wrong. So maybe they rise by 2.5, maybe they rise by 4, maybe they rise by like 3 inches, maybe they rise by 15 feet. Like, we can't be sure. We just have a reasonable amount of confidence that sea levels are going to rise. We have a reasonable level of confidence about how much the sea level is going to rise. Now, here's what's interesting about this when you get into the politics. So this is the science part of it, and you can look at the data. We can evaluate the quality of our models. We can revise predictions. There's all sorts of stuff that we can do and just stick with science. Where we get into the politics of it is when people are trying to be persuasive. They're trying to get you to do something or somebody else to do something. And I'm going to characterize the politics the way that I think would be really useful for you to think about this is that there is no good guy and there's no bad guy in politics. Right? Politics is about persuading, right? You're persuading people to vote a certain way, or you're persuading people to act in a certain way. And so no matter what you do in politics, you're likely to see something like this. If you have a prediction, if I have a prediction and I want to convince people that my prediction is going to work really, really, really well, and that they should do what I think because my prediction is going to work really, really, really well, then I talk about my prediction from a scientific standpoint the way that we talk about something called projectile motion. So projectile motion is how things move when they're flying through the air. Okay? Now, I will tell you right off the bat, I am terrible catch. I can't catch. I just am not very coordinated. But most of you are more coordinated than me. And regardless of whether or not you're more coordinated than me, every single person in here could accomplish the following task, okay? I'm going to throw this tennis ball, okay? And I'm going to throw it to Colm. And here's what's going to happen, all right? Now, Colm, you might not catch it. But you're not going to put your hand somewhere and the ball is going to go somewhere completely different. Like, your hands are going to be near the ball. You'll probably hit it. If you don't catch it, it's going to hit your hands, you know, or like, you're going to be close, right? So let's try that. Ready? Okay, so there we go. So it hit his hands, bounced off, but he knew right where that ball was going. And here's what's interesting about that. Those of you who play any kind of sport that involves like a ball or frisbee or whatever, you know this. As you get good, you know intuitively where these things are going to go. you don't even have to think about it. You can make a really, really accurate prediction. Is your prediction perfect? No, it's not. If you watch somebody catch a ball, especially if it's thrown really far, really fast, you'll see they put their hand up, like if it's a baseball, right? Put their hand up, and then they move, they adjust, right? Because their initial prediction isn't right. But their initial prediction is darn close. And that's because projectile motion, our internal human model for projectile motion, is so good that about 99% of the time we know right where something is going to go. Okay? So if I want to persuade you that what I'm doing, what I'm trying to get you to do is like solid information, then I emphasize the fact that I have a model that works almost every time. But if I'm trying to convince you that something isn't very accurate, I can use the same model, the same ideas, and I can use, like persuasive skills, that's what politics is all about, to try to get you to have some doubt. So I am now going to throw this crumpled up piece of paper. This crumpled up piece of paper will be flying through the air, just like the ball was. I absolutely guarantee that nobody in here can make an accurate prediction about where this is going to be. Now, it's possible that under the right circumstances, I could throw it and you could catch it, but it wouldn't look nearly the same as if I threw a tennis ball and you caught that, right? When I throw this, I'm gonna throw it at Olivia, and here we go. Are you ready? And I'm gonna throw it hard, so get ready. Prepare yourself. Are you ready?
Yeah.
Did you see what she did? That was perfect. You moved in such a way as to catch something if it had actually been a ball. Like if that had been a tennis ball, you probably would have caught it. But it's not. It doesn't move like a tennis ball because it's the wrong shape. It's light and it had all these like flaps sticking off of it, so it's like getting affected by the wind. It didn't go very far and it didn't go in the right direction. It like turned and slowed down really quickly. It was impossible to make a good prediction about that. That's what happens with the politics. When people want to persuade you to like do something like to protect the planet against climate change, they show you things like, oh, these glaciers are shrinking, and here's this graph, and so this is just what we thought was going to happen. When people want to persuade you that there's nothing to worry about, they point out that, like, last winter was a record-breaking winter in terms of snowfall in California. So if there's like global warming, then why is it that like that was the snowiest winter we can ever remember in California? Like how does that happen if the Earth's temperature is increasing? And the answer is neither one of those things in and of itself is particularly meaningful. The only things that are meaningful are what sorts of predictions in general are our models making, and as time goes by, are we revising our models so that they become more and more accurate? We're going to spend a bunch more time talking about this stuff. Okay, we're going to spend a bunch of time talking about models, and you will be working with models. But for now, what I just want to do is make sure that everybody understands that while that video was visually stunning, while the data that they presented was entirely accurate, there was a political angle to that video as well. And my goal in this class is not to indoctrinate you into any particular political realm, but to present the science. So when we look at climate change later, we're going to dive back into it in a couple months. When we look at it later, we're going to look at data and models and science, and we're going to forego the political piece. All right. Okay, so on Friday, get yourselves ready because we're going to launch into pH. We're going to go back into biochemistry. We're going to talk about pH. You guys are going to measure pH of a bunch of things using, cabbages, and then we will proceed. Yeah, you heard me. And then we'll proceed apace to making sure that you guys are ready to start doing some experimental work with with a certain kind of biochemical substance called an enzyme, all right? Yeah. Can I have your chasing ice sheets? Just bring them up, pile them up on the desk up here, and once you've done that, you can take off. Have a great afternoon.